a todos. En la noche buenas noches. Para buenas noches para todos, bienvenidos. Esta es la sesión académica de ASOCOLPAT. La noche de hoy tenemos un invitado de lujo, gracias al enlace que nos realizó el doctor Jaime Mejía, nuestro expresidente de ASOCOLPAT, y quien nos va a acompañar como nuestro anfitrión en la noche de hoy. Doctor Mejía, queda en sus manos la sesión de esta noche. Jaime, ¿no se está escuchando?
Ya. Yo lo que decía era que ahora sí me escuchan, ¿no es cierto? Lo que decía era que se siente uno como en un espejo porque estaba hablando el doctor Mejía, y el doctor Mejía saluda al doctor Mejía. Entonces, gracias Juan Carlos por esa introducción. Ahora, para no demorar tanto, yo voy a mencionarles brevemente quién es el doctor Dibson Gondim y qué es lo que vamos a tener como conversatorio y como conferencia durante esta noche. Parte de esta introducción la vamos a hacer en inglés porque hay una audiencia mixta de personas que hablan español, hay una audiencia de personas que hablan en inglés. Para el doctor Dibson Gondim es más fácil comunicar sus experiencias académicas en inglés, aunque él es de origen brasilero y obviamente su idioma natal es el portugués brasilero, pero el conversatorio que vamos a tener es muy bien estructurado, no queremos interrumpirlo, entonces no va a haber traducción simultánea, ni va a haber traducción en tándem para no demorarle el tiempo, no quitarle tiempo y no quitarle fluidez a la presentación, o con las herramientas que hoy en día también es relativamente fácil todo esto. Entonces, sin más preámbulos, this is here with us is Dr. Dibson Gondim. He serves as an associate professor of pathology and also as the director of pathology informatics at the University of Louisville in Kentucky, several miles from here. He's also in anatomic pathology, neuropathology, and clinical informatics by the board certified by the American Board of Pathology. And I'm going to jump on this long roster of achievements to the most recent one that is very satisfactory. In that year 2019, guess there was the USCAP meeting. He get the award of the Surgical Pathology Award for his work as in the classification of kidney tumors using artificial intelligence tools. He also was he received the Bessie Friedman Award at the Association of Pathology and Informatics, and recognition for his work in digital pathology. So, with no more words, Dr. Gondim, thank you for accepting our invitation, and the time is all of yours.
Thank you very much. I'd like to thank you everyone for this opportunity. It's an honor for me to be here and to give this presentation. I think this is a very important theme, and we're going to talk about kidney tumor classification, but more importantly, we're going to talk about how informatics can help us and how AI and computational pathology will help us to advance the field. So, thank you again for the kind introduction. And I have no disclosures. So we're going to talk about how image-to-image search can revolutionize the diagnosis of rare cases. This can empower non-specialist pathologists to confidently diagnose rare cases. We're going to talk about principle, and I'm going to show you an implementation example. So first, I would like to invite everyone to begin with a story. And this story happens in a remote tropical coastal city. More precisely in Colombia. So the star of this story is a Colombian pathologist. And he was having a calm, very happy day of work, especially because the day before, Colombia defeated Brazil. So he was still thinking about the game when he came across a very challenging case. So it was a 4 cm kidney tumor in a 36-year-old female. That's the low power of the tumor. We see that this is a well-circumscribed tumor, and the tumor has a thick pseudocapsule. Looking closer, we see that on the left side, the tumor has some solid areas and some cystic areas, and we can appreciate that the kidney parenchyma does not appear to have any changes. This is a very unusual tumor. He never had come across a case like this. So essentially, there are cystic structures and there are some solid areas. The cells are really bland, and there are occasional calcifications, and he was not sure what this was. So thinking more about the tumor, obviously, every time you have a kidney tumor, the first thing that you consider is a clear cell, and this is not a clear cell. This is not papillary, not a chromophobe, so on and so forth. And he ran out of options, and he decided to call the clinician and tell the clinician that it's not even clear if this is not neoplastic or not. Overall, it appears to be benign. He cannot rule out, however, since he doesn't know exactly what it is, he needs to rule out he cannot rule out a malignancy, and he would need to send the case for consultation. So the case goes to a major city, and in the meantime, we have a patient that talked with the clinician. The clinician explained that they could not rule out malignancy at this time. which can create a lot of suffering. But then the case was evaluated by a lot of senior pathologists, and someone came with an answer, which is this tumor is similar to atrophic kidney. This is the tumor that's similar to atrophic kidney parenchyma. This is the atrophic kidney-like lesion, which is a benign tumor. And this is a very rare tumor. So there is a case report and literature review that shows here. We see that this is the same tumor. And the review of the literature only reviewed 16 cases. Let's contrast that with clear cell renal cell carcinoma, that worldwide there are 500,000 cases every year. So these rare cases can be very challenging to the general pathologist, and sometimes it can be very challenging to the expert as well, which can make diagnosis extremely challenging. This particular case, because it has not been formally recognized by the WHO yet, is not present in the WHO and it's not present in major pathology textbooks. So rare cases may require extensive workup. And that's where image-to-image search can really help us could have spared us of all of this drama. So the idea would be to have a tool that you have an image and you try to find the best match, and the tool would be able to give either the correct diagnosis or a small list of diagnostic considerations that would guide you towards the workup. And if a solution like that was available from the very beginning, a lot of effort could have been spared, and the patient could be spared of all of the weight. So to put such a system together, we're gonna delve into the informatics portion of the lecture. We're gonna need a couple of different components. One component is a vector database. There are explanations and illustrations in several slides, but let's begin with this one. So a vector database is a specialized system that allows storage and searching of high-dimensional vectors. This enables similarity-based search. And a vector database will become a critical component of the lab of the future. You may not have it today, but some years from now, it's for sure it's gonna be implemented in many places. So why they matter in pathology? Pathology data is inherently visual and complex. And now we have powerful AI models that can create semantically meaningful representations as vectors. So use cases. How do you use a vector database? One use case would be to find similar histology images. Another use case is actually multimodal search. We're not going to cover the subject in this lecture, but it follows the same principle. What would be that? If you have a specific molecular result, you could potentially search images from molecular results, or from text, you could search molecular results from images. So multimodal search would allow you to go from different directions. You could start with the molecular data and end with an image. And obviously, this would be an amazing tool for decision to support if it's able to retrieve cases with similar morphologic patterns. So the three main components for creating a system: one is the vector database. 2, we need to talk about semantic image retrieval. And 3, we're going to talk about how foundational models allow us to create vectors that are meaningful. So, what is semantic image retrieval? The idea is to retrieve candidate images like the query image. You have an image, you want to find images that are similar. So, successful retrieval consists of images that have semantic similarity. What is semantic similarity in pathology? Would be either same diagnosis or same tissue or same architecture, among others. Okay, so let's explore this concept first. Let's explore the concept of image similarity. What is image similarity for us? And then we talk about what's image similarity for the computer. So first for us, let's begin with an exercise. Let's say that we have this query image and we want to determine which one of the candidate images looks the most similar. So if we do this exercise, I would say that image 2 and 5 appears to be the most similar to the query image. So let's talk about, so what would be an acceptable similarity approximation? This is the target image. And these would be acceptable. These images are, somewhat similar, and these other images are less similar. And then if we explore the diagnosis and architecture and cytologic features, the perfect match actually is this image here on the right. It's the same diagnosis, same architecture, and same cytologic feature. This image here has the same architecture, but it's a different diagnosis, and these images here have several differences. So I would say that an ideal result would be, this would be the most similar image. This would be the next one. And these 3 would be the less similar image. So if we put together a system that give us results like that, then the system would be able to help us on classify renal cell carcinoma. So, for example, so this is the idea. One, like you have a query image, like the image on the left, and then you have a database with a large number of images. So how would be a search-based classification? A search-based classification, you'd have the query image, you interrogate, you query the database, and these are the 3 most similar images. You look at the labels of the images. We know the labels of the images that are inside the database, and these images have, the 3 of them have the same label. So based on this method, this image would be classified as papillary renal cell carcinoma based on similarity. In pathology, there are different types of image formats, and there are different types of search. You have regular images, you have whole slide images, and based on that, you're going to have 3 main types of search. You have image to image search, you have image to whole slide image search, and you have whole slide image to whole slide image search. So the details here is, if you do image by image search, the target image is going to be either a photomicrograph or a patch from a whole slide image. The database will contain photomicrographs or patches, and the retrieved image, it's going to be a photomicrograph or patch. The image to whole slide image search, you start the search with a regular image, and the database actually contains patches of the whole slide image with the coordinates. And the retrieval would be the specific whole slide image with the patch coordinate. And the third modality is whole slide image to whole slide image. And again, like you'd have like patches of whole slide image is the target image. The database has vectors from the whole slide image. And then the retrieval would be a pointer to a whole slide image. Having said all of that, so we know how we understand similarity, how we can determine how an image is similar to the other. How about the computer? How the computer calculates similarity? How this is done? So the answer is vectors. So vectors, you can measure image similarity with vectors if vectors capture the semantic features of the images. So the idea here is distances between the vectors can be computed to quantify similarity. And of course, this only works if the vectors capture key features of the images. Then in this case, shorter distance implies similarity. And then pathology images can be encoded as vector using many different techniques, but nowadays we have many pathology foundational models available, and the pathology foundational models do create high quality representations. So this is how we see this problem. We see an image and we imagine a database full of images. And then, but the computer sees this a little bit differently. It sees a vector and the database is full of vectors. Now we understand why we need to use a vector database if we need to search. So if you have a vector, you have many ways that are different distance metrics, that are different kinds of distances, but just a short experiment here, we have the query vector that's located in the X7 position and Y8 position, and we want to know which one of these vectors are the closest. So we could plot this. Remember that our query vector is this one, is X7 and Y8. This is the query vector. And the vector number 3, we can see here that's the closest. And here, vector number 3 has the closest Euclidean distance. So pretty much that's what the computer do. As long as the computer encodes the images as vectors, and the vectors are able to have is able to capture the semantic features of the images, such a system would work. So this is also called content-based image retrieval. And again, our goal is to find images that are similar in meaning and content. Why I keep saying meaning and content? Images can be similar for other reasons. So if we see here, let's say that let's talk about the dogs. So here we have dogs and we have a cookie. In terms of colors, the color of the dog and the color of the cookie, even the distribution, like you see the black, if we are not talking about meaning, if we are just talking about texture and colors, these would be the closest images. However, given that the pathology foundation models are able to extract the meaning of the features of the images, they usually cluster together images with high semantic similarity. So this is the type of result that you want, like the dogs being clustered with the dogs, or the clear cell renal cell carcinoma clustered here and the other tumor distant. So if we see here, this is close, and tumors that belong to another class would be distant. So the next step is how to extract features of an image as a vector representation. How do you do that? You have an image. So what you need is an encoder. So you have an image, you're going to have an encoder, and then the encoder will transform the image in a vector. There are different types of encoders. The most common backbones are the visual transformers, the convolutional neural networks, and the autoencoders. And there are several different types of training approaches. So now what we call pathology foundation models are encoders such as vision transformers that are trained in a very large number of medical data without any labels. And these models are able to capture the semantic meaning of the images. So here is a list of the most common foundation models. We have many nowadays. And the output, if you give an image to any one of these foundation models, you're going to have a vector. Some vectors are from about 400 dimensions to 4,000 dimensions. So, for example, the Verco 2 foundation model, the vectors have over 3,000 dimensions. For this experiment, I'm going to use the model that was a collaboration with Microsoft. That's the ProGigaPath that has 1,536 dimensions. So when I give an image to these foundation models, I'm going to get a vector of this size. So the idea now is to show you an experiment on how I use this to classify kidney tumors. So the idea here is a multi-class kidney tumor classification. The search type is combination of patches to patches. The encoder will be the pathology foundation model ProGigaPath. And the validation strategy is going to be leave one out. We are going to illustrate several of these principles. So I used a total of 137 slides, and there is a couple of things that I want to highlight. One, some of the classes, such as the atrophic-like kidney tumor, which was the tumor that was causing trouble in the beginning, we only have 3 slides from 3 different patients. And if this works, it would be great because it's usually very difficult to put a large number of slides together for tumors that are very rare. So again, where can we read about these encoders? Here is the reference about the ProGigaPath, and actually you can download and you can use the ProGigaPath to do research. It's available in Hugging Face. So what I'm showing here, you could try yourself. So what's the pipeline? The next step is we have a lot of whole slide images. We want to get a database populated from these whole slide images. So in the left here, we begin with the whole slide image. The next step is tiling these whole slide images into patches. After that, we get a patch and we use a foundation model to extract the vector. Now we have a vector, and once you have a vector, you can put the vector in a vector database. So this is the pipeline to create a vector database with pathology images. Again, there are many different types of pathology foundation models. These are models that are newer models, and they are used in many research projects. Usually these models are trained with over 100,000 whole slide images. I believe that Verco 2, it's over 1 million whole slide images. And they outperform the ImageNet baselines. They outperform the other approaches. They are able, they are better at capturing the meaning. So this is the result that I got from this experiment. So we have these high dimensional vectors, if we want to visualize where the vectors are clustering, we can apply dimensionality reduction techniques and see if that, and we see here that actually the patches form several discrete clusters. This is a great result, and this tells that probably if we try to classify tumors based on this approach, it's probably going to work or have high accuracy, because the clusters appear, there is a single class that dominates most of the clusters. So this was you can do UMAP. This is a UMAP projection, and this is like the validation of the morphological clustering. So here it's, when we see this, it's not, it's not very, I wanted to create a visualization that was more concrete to a pathologist. So I transformed that visualization in this other visualization here. And I'm gonna show you how that looks in terms of the images itself. So we can see here that we have multiple clusters. Images are clustering together. We have the patches. All of these patches were extracted from those 137 cases. So if you go here, this is the patch of the atrophic-like kidney tumor. And you can appreciate that there are no patches from any other classes here. There is no contamination. And if you go here, you have patches of renal calcitoma, and there is no contamination. And you have different renal calcitoma here. And let's see this here. This green is clear cell renal cell carcinoma. The interesting thing about these particular patches, these are clear cells that have eosinophilic cytoplasm here. If you go here, we see clear cell with more classic morphologic features. And here we have more of the atrophic-like kidney tumor. We have 9 categories of tumor here. Let me show you this one. This one is the fumarate hydroxylase deficient renal cell carcinoma. And what else could we see here? This is a case of metanephric adenoma. The main point here is that clustering is very consistent. There is very little contamination, and this result tells me that the foundation model are really capturing the meaning of the images. Okay, once you have the vectors, if you have a lot of vectors, you're gonna need a vector database, because otherwise you're not gonna be able to do fast searches. It wouldn't be scalable. Let's say if you're not using a vector database, if you have a collection of 1 billion vectors and you have a new image and you want to know which image is the closest, you'd need to calculate the distance between this vector and 1 billion vectors every time. And vector databases have several optimizations that allow us to do these searches very fast. So it uses approaches such as, instead of k nearest neighbors, which would be the perfect calculation between one image and 1 billion images, it uses approximate nearest neighbors that take shortcuts to do the calculations. And there are many other advantages of vector databases. The bottom line here is, if we wanted to create a database for pathology, eventually you'd need to implement one of these databases. I used the PyCon database, and this is the configuration that I used. One of the configuration aspects is the dimensions of the vector, and this is the dimension of the vector of the pro-gigapath. The next illustration here is in this situation that I have some types of tumors, such as, let's say, papillary renal cell carcinoma. I have 43 slides, and atrophic like kidney tumor have 3 slides. We need to use a validation method that ensures that there are no contamination of the images. What's contamination? Contamination should be an image of a case. You search images, and there are some images of the case that you search inside the database. And obviously, if you have some images in the database, you're going to have a good result. So we need to ensure that there is isolation between the case that you're searching in the database. So leave one validation method. We create one experiment for each whole slide image. So for example, this is a simplification. This would be the first experiment. We get this case here, clear cell number 1. We put clear cell number 1 on the side, and you get the rest of the cases to create the database. And then so on and so forth. For the second case, we will do the same, and we would need to do, in this case, 137 experiments to prove that this works. And after that, so how this works? Again, you have the target case, you have the vector database, and now you want to know where the images of the target case will land in the vector database. So, for example, the first image, if it lands it there, given that the patch is close to its clear cell, we would classify the first image as clear cell. If the second image lands here and the images around are papillary, this would be papillary. And then the other one, clear cell. You can see that we're going to do this exercise for every single image. And the final classification result or differential diagnosis is based on, first, the most common the most common patch would be the final diagnostic label. So if most of the patches indicate that this is clear cell, AI would be classifying this as clear cell. The way to determine the performance here is to do this experiment for every single case. And if you do that, this is the results that you get. This is the the confusion matrix. And in this column here, in the diagonal that's green, these are all cases where AI was able to classify the cases correctly. So we can see in our first example, the atrophic like kidney tumor, all the cases were correctly classified. For one case of atrophic like kidney tumor, there were 2 other cases inside the database with all other kinds of tumors, and the patches always landed in the atrophic like kidney tumor area. So what's the slide level classification performance? So in this experiment, AI was able to get a top 91% accuracy. And what's very interesting for us too is the top 3. Top 3 is the 3 most likely diagnoses if the true diagnosis falls under one of the 3 most likely diagnoses. So when you do that, cases, you're gonna have, oh, this case has this percentage of clear cell, has this percentage of papillary, has this percentage of this. So if we include the 3 highest percentages, if the goal is a differential diagnosis, the list of the 3 most likely differential diagnoses gets right almost 100% of time. And this is the weight sensitivity and weight specificity. So clinical applications, obviously, this can be used for decision support for rare cases, could be used for quality assurance, grading consistency, tumor board aids. There are many applications for research and education. One could use this to assemble cohorts and peta discovery, biomarker research, teaching atlas. There are also a lot of challenges, and this is still this is still an emerging topic. And one of the challenges are reindexing new encoder. So let's say that you have 1 billion images, and you use a foundation model to encode all of these images. It takes quite a bit of processing power to do that. It may take, maybe 1 day, weeks. It depends on the amount of computational resources you have. And let's say that in the next week, there is a new pathology foundation model that the authors claim that's much better. If you want to use that in your database, you're going to need to extract all the vectors again. So this would be reindexing. For every encoder, if you want to do search based on a new encoder, you need to reindex all of the images. So there are issues related to scalability and resource consumptions. Other things is that would be very important would be we need to ensure that these systems are integrated in the hospital workflow. So in the ideal situation, you have a digital pathology environment, and you are looking at your whole slide image, and there is an area that you want to know what are other images that look like this. You'd press a button and you'd get results right away, rather than transferring an image to another system or uploading image. So in the ideal situation, these systems need to be integrated to get the highest value. Standardization speaks for when we are talking about creating a database for multiple hospitals. Obviously, everyone would need to use the same encoder. So an experience with reindex, let's say that you have a database with 1 billion patches, you have a new encoder, you need to recreate vectors from scratch. Do you keep both indices? Do you keep the old one, or do you throw away the old one? For how long? If you have this GPU, it would take 7 days to encode 1 billion patches. And one of the things that we want to achieve one day would be to have a unified database where we would be able to search for similar cases eventually anywhere in the world. And one of the challenges related to this would be to for an agreement on the encoder. Once we have, everyone would need to agree on an encoder or a few encoders to make sure this is scalable. So vector databases are really poised to become a key component of healthcare technology infrastructure. One of the goals of this lecture is to talk about the fundamentals and how they work, because understanding is essential for their effective application. Foundational models enable powerful generalizable representations of pathology data. And this is the type of technology that supports innovations across the clinical, operational, education, and research domains. These are some of my references. And I would like to thank you, everyone, and thank you again for the invitation. I'll be happy to take any questions.
Okay, we will wait if we see some questions. In the meantime, I want to thank Dr. Dibson Gondim. Thank you, Dibson, for sharing your expertise with us in this field, that all pathologists, we should be embracing this as part of our tool case in our day-to-day approaching to our specialty. So also, I want to thank the Asociación Colombiana de Patología, especially Dr. Juan Carlos Mejia, who was the previous president of it, now is the director and coordinator of academics and education, continual education. He was also a previous director in the pathology in the National Cancer Institute in Colombia. And we appreciate that he has endorsed this effort, and obviously the leadership of Nalest and Dr. Lu Sua, who is the president of the association. And last but not least, also thanks Lucy for the technical support in this. So if there's any questions in Spanish, and I don't know if you wanted to hear it directly in Spanish and reply to it, Dibson, you tell me, or if you need any, if you need any translation for it, that would be fine. There's Dr. Rafael Parra Medina, who's also the director of pathology in the National Cancer Institute in Colombia. In the meantime, also, I was talking before the broadcasting with Dr. Gondim about, this is a new field, and actually we need to learn a new language, and there's a process, there's a learning curve in this. For some of us, is something completely new, but we are really positive into it. In my case, for example, it's been like almost 4 years that I don't use the regular microscope. I quit it like 4 years ago, and I never go back to the regular or usual microscope. I love USI, all the tools that we can do, and now we are using also a very rudimentary artificial intelligence, obviously. But for the new generations, and for all those who want to get into this field, how can you give us some advice? How can we proceed to get the best information and to be prepared for it, and also taking advantage of your position, maybe be a contact for the new generation of pathologists in our Latin American countries and some others that are also joining us in this speech. They want to pursue a career or special in the spatial field as you have done.
Yeah, it would be a pleasure to support pathologists in Latin America, worldwide. So this field, there are good resources. Some resources that I can point out is the College of American Pathologists, CAP. They have the AI committee, and there are materials and there are lectures. There is also the computational pathology in the CAP. Also, there is the DPA, that's Digital Pathology Association, and they have webinars and many educational materials in their site. And also, very important, Association of Pathology Informatics. So these are the three main resources: CAP, College of American Pathologists, DPA, Digital Pathology Association, and API, Association of Pathology Informatics. We're gonna have a meeting about digital pathology and AI in November in Chicago on the Association of Pathology Informatics. And obviously, US CAP has also pretty good research material. But anyone who would be interested, feel free to contact me. And the other thing is the Brazilian Association of Pathology. It's putting together a series of lectures. It's gonna start soon and go throughout the year. They're gonna be in Portuguese, but I believe maybe some of them are in English. They're gonna be a great resource too. So check the website of the Brazilian Society of Pathology.
Okay. Dr. Rafael Parra Medina is asking if you are using PathChat in your practice.
So our practice at University of Louisville, we have a robust digital pathology infrastructure. We scan pretty much all the slides. We use Page. So our viewer is Page. So we don't use PathChat.
PetChat is works like a chatbot, something like that, maybe.
Yes, I've seen presentations. It looks like it's a very interesting tool. Looks like a chatbot for pathology. It I remember that it helps with synoptic report, finding areas, but I don't know all the details. But it's a chat-based tool.
Do you think that this technique that you well, I don't know if it's the right word to use, or this tool, or these model of searching image to image in that you have shown us before, is it better to be used clinically? I mean, we can say it in a report or something. We use this technique to approach this diagnosis. It has some validation or any other form or normalization by any one of the agencies?
Yeah, this technique, it's very new, has not been fully implemented. I'm not aware of a clinical implementation. I think that the main idea here is to provide some guidance to the pathology, to point the pathologist in the right direction, rather than being the diagnostician. So it's a tool to help us rather than to replace us.
Yeah, that's been always the usual question, and we're going to be replaced by the AI. I hope not, because if not, I don't know what I'm going to do. I hope I'm going to be out of the market soon. But anyway, I think we can embrace this as a technique. If you don't mind my insight about this, maybe you share too. But on the other side, I was wondering, how can you foresee in the near future? Because I know that maybe in the long term, these tools and these techniques will be everywhere. But in the near future, I think that we are moving more into the diagnostic stewardship field than being like the morphologic experts as we used to were required before. But what do you foresee as an expert in this field is the near future advance in pathology in this field?
So these tools can also provide higher degrees of automation, right? So, for example, there are tools there are similar tools that are tools for cancer detection. So it's a tool that if a slide has cancer, has malignancy, the slides are flagged. So this type of tool could be used for prioritization. A tool like this one to search for images, if this gets incorporated in a digital pathology pipeline, there is the potential that for every single case, you could get a list of differential diagnoses to begin with. And, you could also use that for triage. So I think the key here is to integrate these tools in the clinical workflow in a way that makes it easy for the pathologist to use. Unfortunately, there are very few examples nowadays of that. For the most part, the solutions live in different applications, and you need to do different logins. But in the ideal situation would be to incorporate this tool and similar tools in an integrated fashion.
Okay. And about the education, about the formation of new pathologists, well, this is a field that it requires a lot of preparation and a lot of also intelligence. But what I mean is, I think that is maybe are we gonna have to have like a pensum or something in our syllabus and the formation of our residents that is mandatory in terms of pathology informatics in the near future? Making the specialization a little bit longer, or do you think that maybe it's going to be like a new subspecialty mostly?
No, I think this would be like one of the foundational knowledge, almost like knowing how a antibody works. If you know how a antibody works, you understand when it doesn't work and how to troubleshoot it. I think education is essential, because if one of these systems, let's say there is a day that's not working, if you don't really know the basic principles about the system, how are you able to troubleshoot? So I think it's fundamental for the pathologist to have at least basic knowledge about this. There are opportunities to develop more advanced knowledge. The other things are, there are a lot of, even if you don't have digital pathology in your hospital, there are a lot of digital pathology research resources in the internet for free. One is the TCGA. If you type in Google TCGA, you're gonna be able to find pathology results, and also the papers. You could try to replicate some of the papers. So again, like this knowledge, I think the basic, it's fundamental, and Association of Pathology Informatics has a curriculum, and there are a lot of opportunities in the internet to develop these skills, but it would be more like a basic knowledge, I believe, rather than something that is specialized, unless you do research.
And what about the implementation of these kind of techniques to solve two problems? Those areas that are underserved pathology services and the shortage of pathologists. Maybe we should be also curtailing a little bit the formation of new pathologists, knowing that there will be more things done automatically this way.
Yeah, so the challenge with the underserved areas is the resources. Because at this moment, these technologies are still very expensive. So it's possible, it's always possible that someone tries an implementation based on, let's say, an implementation based on pictures taken with the cell phone. For example, we could have a database with several images, and if you want to check the database, you could check with taking a picture with your cell phone. This is not well studied, and it's not clear if this would work. But, this is something that needs to be explored. So this would be, if this technology becomes available and it's functional on cell phones, I think this can help a lot underserved areas. But the challenge there is actually the resources, and the technology is still very expensive.
And about the shortage of pathologists that are all over the world.
Yes. So if the technology gets implemented, so with triaging and with like drafting reports up front, you're gonna be able, there is a potential to increase productivity. Even like, one could create systems, and there is work like that. So for example, AI sees an image and decides whether it's gonna order stains or not. So one could use AI to increase the productivity of pathologists. Now we are not there, and we are not there because there is not a lot of integration. But eventually, when we have both AI and integration with clinical systems, I think we're going to be able to take advantage of higher productivity.
Okay, great. Thank you, Dr. Gondim, for for sharing your expertise with us in this hour. Again, thanks la Asociación Colombiana de Patología, Dr. Juan Carlos Mejía, Dr. Luzua, who is the leader president now, And thank you all who joined us tonight. People were from Peru, from Brazil, people from the United States of America, Colombia, obviously, and some of our neighbors also, I think Panama, Venezuela, and so on. I hope that we may see you again with us. If not, our paths cross in any of these meetings. And appreciate that, Dr. Gibbs, Dr. Gondim, for this. Thank you so much. And thanks and good night to everyone.
Thank you very much again. Buenas noches.
Buenas noches. Okay.
Bueno, buenas noches. Nuevamente el agradecimiento de parte de la Asociación Colombiana de Patología al doctor Gondim y al doctor Mejía por haber actuado de enlace y habernos conseguido esta excelente presentación. Vamos a finalizar la sesión con unos anuncios importantes para la comunidad de patólogos. Los estamos invitando a inscribirse a nuestro curso virtual que es completamente gratis para los asociados a ASOCOLPAT, Perspectivas en el diagnóstico y manejo de HER2 bajo y ultra bajo en cáncer de mama. Este es un curso virtual que va a tener una sesión en vivo final el 28 de agosto del 2025. Los invitamos entonces a que aprovechen esta oportunidad. Es un curso muy bueno que toca un tema muy actual y que creo que va a servir para nuestra comunidad de patólogos. Y finalmente la invitación al 6º Congreso Colombiano de Citopatología a realizarse del 23 al 25 de octubre en Cartagena con unos invitados especialísimos de actualidad completa en el tema de citopatología. Así entonces damos por terminada la sesión. Hoy tuvimos nuestra primera transmisión en Instagram y es una de las nuevas redes que estamos utilizando y así logramos abarcar muchísimo más público dentro de nuestra comunidad. Muchísimas gracias y los esperamos en la próxima ocasión.